So this is going to be our beginner class on antennas. So antennas for beginners. Now, as amateur radio operators, we need to know something about how our antennas work. So we're going to go ahead and jump in. First, let's talk about what an antenna actually is, or what is an antenna, right? I've got some example antennas on this slide, but we're going to talk about what it is. So basically, let's think about how the radio works, right? If I've got my radio, it's going to take some kind of input. It's typically going to be audio, me talking, right? It takes that audio signal and converts it into an electrical signal. Then the radio amplifies and modulates that signal at a particular frequency and sends it out through the antenna port. So there's usually a little jack or something on the radio, and that's the radio's job, is just to get the signal to that point. Then you've got a feed line or piece of cable that connects the radio to the antenna, right? And sometimes there's an antenna tuner in between. We'll talk about that later. There may be a matching transformer, balun, or some other device at the radio. We'll talk about matching in a bit too. The antenna accepts those electrical impulses from the transmitter and emits them into the air or into space, or however you want to think about it, right? So on the receiving side, these signals are just floating around out here in space, right? And the receiving antenna does the opposite. It collects those signals and feeds them back to the radio. And then the radio has to filter out the stuff that it doesn't want, amplify the signal that it does want, convert it back into audio through a speaker, and deliver it to your ears so that you can hear what's happening, right? So that's basically how the radio works. This is an example of a simple amateur radio station. Simple, right? So what you see on here, we've got the microphone, we've got the transceiver. So everybody know the difference between a transceiver, a receiver, and a transmitter?
Transmitter just transmits.
Receiver just receives. Transceiver does both, right? So it's like having two radios in one box. You've got a transmitter and a receiver in one box. Now, on this one, they also show another input mechanism called a keyer, and they have a key and paddles hooked up to that. That's for what we call CW, or Morse code, right? So the way that typically works, and typically if you have a straight key like that, they show a key, that's typically connected directly to the radio. It doesn't usually go through a key or device, but the paddles are connected to a device that accepts inputs from the switches on the paddles and converts it into nice, well-formed dots and dashes. So we're not going to talk a lot about CW or Morse code, but just understand that with a key, when you push it down, it's transmitting. When you let go, it's not. With the paddles, when you apply one of the paddles, it makes dots. When you apply the other paddle, it makes dashes. And so by controlling which one you're pushing for how long, you get a mixture of dots and dashes, right? And that gets fed into the transceiver, which then does the appropriate thing with it. Often nowadays it's built into the radio, right? Back 50 years ago, keyers were pretty much a separate device that you had, and paddles were kind of a new thing, right? But with the straight key, it's just connected directly to the transceiver usually. So the next box in this picture is an antenna tuner. And we're going to talk later about what happens in an antenna tuner. But the main thing to think about here is that it's making sure that as much power from the transmitter side of the radio gets to the antenna as possible. Okay. So that's its job, is to make sure that you get the maximum power out of the antenna. So the next thing we see is an antenna switch, which not every station is going to have an antenna switch, but this allows you to switch your output coax from your radio to a different antenna or to multiple antennas. And I've seen antenna switches with like 4 ports on them. I've seen them with 8 ports on them. A lot of times people will dedicate a port to a dummy load so that if they're doing some kind of testing, they can switch to the dummy load, and then they can transmit without worrying about anything getting emitted, right? But in this diagram, he's got two separate antennas hooked up to this antenna switch. And you can see one of them is on top of a tower, and it looks kind of like a Yagi type antenna or a beam antenna. And the other one is connected to a dipole antenna. And we're going to talk about those types of antennas in a minute. The other things that you see here, there's a power supply that gives power to the radio. There's a set of headphones attached to the transceiver so you can listen to the output. And then they've got a computer down here that's just sitting there by itself, not connected to anything. Not sure what you're going to do with that, maybe logging and something like that. But a lot of stations are going to have a computer involved nowadays. And we've talked about digital modes where you actually have a computer's connected to the radio. The computer is generating the audio signal that gets fed into the transceiver, right? All right.
What kind of software would you have to have for that?
So it depends on what you're doing. We talked about JS8 call last month, which is some relatively simple software that uses a weak signal system to be able to send short messages to other operators. And we've also talked in the past about things like APRS and packet radio. We've talked about some of the digital audio modes like DMR and things like that. Those are all these digital modes where your computer would be essentially acting like a modem and producing some kind of audio signal that is sent out. And then on the other end, the signal gets fed into a computer that decodes it and presents some kind of information on the screen, right? So, all right, so once it leaves the antenna, we've got this thing called an electromagnetic wave, right? And so who could tell me what electromagnetic radiation is? Or give me an example of some kind of electromagnetic radiation.
Light.
Visible light is electromagnetic radiation. What else?
X-rays.
X-rays, also a form of electromagnetic radiation. What one do we care about in amateur radio? Radio waves. We care about radio waves, right? So the frequency spectrum is infinite, right? I mean, it goes basically from 0 hertz or 0 cycles per second, which would be a DC signal. We'll talk about that in a minute, all the way up to gigahertz, terahertz. I don't know what the highest number of hertz that an existing radio system can use, but it goes way up, right? And so this is basically a big range of these frequencies, and associated with the frequency is also a wavelength. And that wavelength defines what band we're talking about. So when we talk about bands in radio, that's what we're talking about. What this actually looks like physically, if you think about it, you've got an electric wave or a cycle. So think about electricity as a voltage, and it goes down and then up and then down and then up, just in like a sine wave, basically. There's also a corresponding magnetic wave that the electric wave produces. And this magnetic wave is at right angles to the electric wave. So together, they make this thing called an electromagnetic wave, and it's actually self-supporting. So what it'll do is it builds itself up. So the electric wave causes the magnetic wave, and the magnetic wave causes the electric wave. So it continues to propagate along. So that's why any of this kind of stuff actually works, is because of this property of these particular waves. So we're not going to talk a lot about how the wave is created or anything like that, but that's basically the idea, is that these two fields, this magnetic field and this electric field, support each other. And this structure, this wave structure, exists not only in the air, but also in the feed line and in the antenna. And it's what the transmitter is creating, and it's what the receiver is decoding in the radio, okay? So let's start out at the beginning. Where does the signal start? Where does the information come from? From the operator, right? Typically, you've got a microphone, you're holding that microphone and you talk into it. Audio vibrations, you know how audio works? It's got like vibrations, compressions and decompressions of the air. And when you're sitting in the room with somebody, those vibrations, so I've got vocal cords in my throat and they vibrate as air rushes past them. And I have learned at a very young age how to manipulate those vibrations to carry information. We call that talking, right? And those vibrations travel through the air until they reach you, where they go into your ear, which is designed to pick those vibrations up, and they make the eardrum move back and forth. And when that does, it pushes on some little bones and things get wiggled around. And finally, a fluidic wave travels through the cochlea inside your ear and moves these little tiny hairs around. And those hairs are connected to nerves, which are hooked into your brain. And your brain, the amazing gadget that it is, can interpret those as some kind of information or sound. And the same way that I learned how to talk, you guys learned how to listen and understand when you were tiny babies, right? So it's really pretty freaky when you think about it, how this actually all works. And so the cool thing about with radio is I don't have to be in the same room as you to be able to talk to you. I can let the radio take care of connecting wherever I am to wherever you are. So I talk, those vibrations hit the microphone, they make something move inside the microphone, and that generates an electrical signal. Well, that signal is going to be varying, right? It's going to go up and down. So let's talk about what happens with that. We have these electrical impulses. They travel down the wire from the microphone into the radio as an alternating current. You guys are familiar with direct current and alternating current? Anybody?
Direct current is like the DC that it goes, where AC is alternating. It's like a sine wave.
Right. So if you think about, so we've talked, in order to get your license, you had to have some understanding of electricity, right? Probably the most important rule for electricity is Ohm's law, and the corresponding, what do they call the power law? So Ohm's law relates current and resistance and voltage, and then the power law relates voltage and current to watts of power, or measurement of power, right? So if you think about a DC circuit, if I've got a piece of wire and I have a battery, the battery is going to produce DC current and I hook it up to my wire. When I make that connection and close that circuit, electrons come flying out of the battery into the wire, and then they go right back the wire back into the battery on the positive terminal. So as I make that connection, a voltage appears in this wire. If I disconnect it, that voltage is going to stop, right? The electrons are going to stop moving. But it's not, it's always the same voltage. If I hook it in, that voltage comes up. I mean, there's a little bit of ramp up time while it comes up, but it's so minuscule you don't even notice it. And so it stays at that voltage as long as the wire is connected. When I disconnect, it fades off to zero immediately, right? So alternating current is like turning that on and off or making that connection over and over and over again. Here in the United States, we use 60 hertz AC signal, which means 60 times every second that power comes up and goes back down again. And in fact, in AC, it not only comes up and goes back down, but it goes backwards and comes back up again. So if you think about the electron in the wire, when the voltage comes up, it moves, and then as the voltage goes down, it stops moving, and then the voltage goes negative, it moves the other direction, and then the voltage comes back up to zero, it goes and stops again. So the electrons in the wire are just kind of going back and forth. They're alternating in position inside the wire. They don't actually go through the whole wire, they just stay there. And what they do is they push on each other as they do this, right? And that's how the power gets transmitted, is by this pushing. All right. So, well, we just kind of talked all about this part. But if we think about this alternating current, it's going up and down, right? What's happening is, as this voltage goes up and down, it can carry information. And the information is carried by varying the amount that it goes up and down, or modulating that signal, right? So we want to talk about modulation. Modulation is modifying that signal to carry information. So if you think about that AC current traveling through a wire at a particular voltage, right? When I plug something into the wall, it's at 110 to 120 volts, somewhere around there. But what if I took that 110 volts and I applied my audio signal to it, so that when there was no audio signal, there was no voltage. But when there was a loud audio signal, there was a high voltage. This is how modulation works, okay? So what we're doing is we're taking that signal and we're making the voltage change to match the incoming audio signal that came from the microphone. Does that make sense to everybody? Give me a high sign if you're with me so far.
It seems like it'd be much easier to do that with direct current instead of alternating current.
So the problem with direct current is it doesn't change all the time, right? So you could vary the current or vary the voltage in a direct current circuit, but it's a lot easier to control it in an alternating circuit. And if you look at the electronics, you'll see what is involved in manipulating the voltage of a direct current source. And it's a lot more complicated than what's involved in manipulating the voltage of an AC source. The other thing is AC takes advantage of some magnetic properties, because as we change the voltage, that change can be converted into a magnetic change, which can change another electrical signal or circuit. And so that's how transformers work. Transformers don't work with direct current because, again, it's hard to vary the voltage up and down. Typically, you have a battery that produces a source of a particular voltage, and you have to do some major manipulations to direct current to get the voltage to go up and down. AC, it's really easy to make it go up and down. All right. Question, comment? Nope. Okay. So now we have a modulated signal that's inside the radio, right? And I've got my information, which is my audio. I've got it encoded into my electrical signal, right? And I can take that and I can amplify it. I can do other things to it. I can manipulate it in various ways. And what I can do is I can apply a particular modulation to it. And typically in amateur radio, we use AM, FM, or single sideband. So typically on VHF frequencies, when you're working with your handheld or your mobile radio, you're typically going to be working with FM. And what FM does is it actually it's called frequency modulation. It actually varies the frequency. Or think about it, if you look at the wave, it stretches or compresses that wave as it's passing through the system to carry the modulation or carry the signal. So the wave is always the same height in FM, but we make it higher or lower frequency to carry that signal. In AM, we use the power of the signal or the height of the wave to carry the information. So it's amplitude modulation. That's what AM stands for. And as you apply more power, the wave gets taller essentially. And when you apply less power, it gets smaller. Single sideband is just a way of stripping out parts of that AM signal that you don't need to actually transmit. In AM, there's a carrier signal that is continuously sent, and you're modulating that signal both above and below that carrier. With single sideband, you get rid of the carrier, you don't transmit that part, and you get rid of half of that signal. So you're only sending like 1/4, you're only using 1/4 of the power that you would need for an AM signal. And it's still a form of amplitude modulation, right? Because the sideband, the signal is still going up and down. We're modulating its amplitude, but it's more efficient. So when we talk about single sideband, what we're saying is we take this AM signal, we mask out the redundant parts of it, the parts that we don't actually need to transmit to reconstruct the original signal, right? comment?
Yeah,
It's hard to visualize, isn't it?
no, it's not entirely redundant, it's just, it's kind of like compressing, like when you're compressing an audio thing or a picture or something, you're trading off a little bit of the fidelity.
You're losing some of the signal, right? You're losing some of the, so that's why we use AM for like AM radio, because we want to carry more information.
The receiver reinserts the carrier.
It does that. Yeah, the carrier is wasted energy, right? But in there may be some of the audio that's going to get clipped off at the high end and the low end, just in the interest of spending less energy to get the signal out, right? If you're listening to single sideband on an AM radio, it sounds like a rubber duck talking, right? It's just, you're only hearing half of what the AM radio wants to hear. And so it kind of loses half of the information. But if your radio knows how to do single sideband, it sounds perfectly normal. Okay. All right. So knowing more about modulation, a little out of scope for the antenna discussion, but you needed to kind of have this basic understanding that we're producing some kind of wave of energy inside the radio. All right. So now we got this modulated signal inside the radio. We need to get it out there so that another radio can pick it up, right? So let's talk about how that happens. So the radio is going to have a little connector on it of some kind to connect to your feed line, or in the case of like a handheld radio, it connects directly to your antenna. And this will typically, on an amateur radio, it'll be an SO239 connector, which is what's in the diagram here on the left, or on a handheld, it's typically going to be an SMA connector. Now, there are other connectors that you may encounter. There are what they call UHF connectors. There's a type N connector. There's a BNC connector, right? These are all different types of connectors, and they're designed for specific purposes. So the Yaesu has an SMA connector on it, and so does the TYT. Interestingly enough, if you look at that, go ahead, show it, Sherwood. Take your antenna off, and Bruce, can you take the antenna off of your TYT? And you'll notice something. The connectors don't actually look the same between those two radios. And that's because one of those is a male connector and the other one is a female connector. You see the difference?
These two are kind of pretty close to the same.
Are they the same? Which Yaesu do you have? The F6?
Yeah, this is the BX6.
That should have a male connector on it. Does it not have one?
Maybe that is a bit.
Yeah,
Yeah, it's good.
yeah. They hadn't been.
Our antennas will have the same pin.
Looks like a female. Well, and I hear from a candidate.
Pin one has a BNC. It's old.
I have an adapter that converts the SMA to BNC for my Kenwood because I like BNC better.
It comes with it as a BNC connector.
Your old Kenwood? Yeah, I think Ragnar, you've got an old Kenwood that has that also, right? Yeah, some.
I had a couple of connectors, so I can put it as a BNC.
Yeah. So they have little adapters that convert from one connector to another, depending on what you're trying to do, right? You may, like, if you wanted to connect your HT to an external antenna, like I did when I was doing the packet radio demo, I connected my Kenwood to a little adapter cable that had an SMA connector. It had a BNC connector on one end and a SO 259, not a SO, a PL 259 on the other end to connect into the cable. No, the other way around. It had a PL. So this is where it gets weird, right? So on the connector that's on the left over here, this is an SO for socket 239. The kind of connector that plugs into that is called a PL 259, not a 239.
military did that.
Yeah, don't blame don't blame everybody, right? I mean, no, it's weird because you would think they would have the same number, but they don't. For whatever reason, the the plug for that is different. But if you have like a type N connector or an SMA connector, you're going to have an SMA male and a SMA female. The male plugs into the female. If you've got a type N, you'll have a type N male or a type N female. If you got a BNC, it'll be a BNC female or BNC male. And the idea is that those two connectors mate together, right? They'll hook together. So we have this connector on the radio. We connect some kind of cable to that. And we call this cable the feed line. There's a couple of different types of feed line that we typically use in amateur radio. You might see something called ladder line used. Ladder line is what's shown on the left over here. You'd see like a big long length of this going from the radio out to the antenna. The other thing you'll see is coaxial cable. If you think of these two cables, they're basically doing the same thing, right? There's one wire that's carrying signal and one wire that's carrying ground or holding the ground. In the coaxial cable, the center conductor is carrying the signal and the shield that goes around that is holding the ground, right? So in the ladder line, the wires are held at a specific distance apart. And that distance apart causes that cable to have a specific impedance. We'll talk more about impedance in a minute. In coax, there's a dielectric or non-conducting layer in between the center conductor and the shield. And that material also has an impedance associated with it. Impedance is measured in ohms, okay? So let's talk about impedance a little bit. So the ladder line impedance is 450 ohms. The coax's impedance is 50 ohms. So why the difference? Why do we care? If you think about impedance, impedance is like resistance. In a DC circuit, impedance is exactly the same as resistance. But in an AC circuit, it refers to how the cable or the circuit responds to the alternating current. It looks like resistance. That's why we measure it in ohms, okay? But it lags from actual resistance. So it follows the wave that is being sent down there. So if you've got this moving AC signal, right, that wire is going to resist that signal to a certain extent. Now, if you think about what's happening in that ladder line, I've got two conductors. So when energy is going in one direction, it's also going in the other direction. And those two movements of energy balance each other out so that the energy can go through the cable without really feeling that resistance. But at the end of that cable is where the resistance actually takes effect once it hits the antenna. The coax is the same way. I've got the center conductor, and when the energy is moving through that center conductor, remember it's moving back and forth, the opposite energy is moving in the shield. And those cancel each other out. So none of the energy leaks out of the cable. Okay. You guys follow how that works? The impedance is measuring how much the cable is trying to stop the flow of the energy, or how much it would stop the flow of the energy in a single conductor. So why was one 450 and the other is 50? We're going to talk about that in a bit. Why do we care about the impedance? If the impedance doesn't match the antenna, some of the energy in the signal gets wasted. Okay. How do we waste energy? We turn it into heat. So typically something will get hot in your system and you won't like that. So let's talk about how that signal is moving along. So the signal is moving along through this wire. It doesn't emit any energy outside of it because it's balanced, right? It's the energy in one wire balances out the energy in the other wire. So everything stays in the wire. It doesn't jump out of the wire. And this, remember, the alternating current in that signal is what's carrying the information that we have. So that's what's pushing this. The information is essentially propagating down this wire from the radio to the antenna. Okay, so let's look at an antenna. This is a very simple antenna called a half-wave dipole. And what we've got here, we've got the feed line that comes up to the radio. In this case, it's a coax up to the antenna. In this case, it's a link to coax, and close to the antenna, the center conductor is broken out and goes to one side of the antenna, and the shield is broken out and goes to the other side of the antenna, right? So if you're thinking about this signal, so here it is moving through the wire, right? And then it gets to the antenna, and now it gets separated out. So what's going to happen? That energy is not going to stay in the wire anymore because it's no longer balanced once it hits that antenna, right? It's actually physically separated. That's when the energy gets radiated from the antenna. Okay. This is one of the concepts that hit me like, I understand now what is actually happening when I get to a dipole. It's as if I took my ladder line, right? My balanced ladder line with the current moving back and forth, and I split it in half, and I dragged half of it out this way and half of it out this way. This is why the ladder line is 450 ohms, because the impedance of the antenna is 450 ohms. I don't need anything to match that in between. When I'm bringing that signal on coax, I need some length of separation between the actual coax and the antenna in order to make everything balance out. And this is where you'll find things like a matching transformer, or what they call a balun. A balun's short for balanced to unbalanced. And it's usually it's a little coil, and it actually takes that and matches that balance signal to the unbalanced antenna. Okay, so I said it was a half-wave dipole, right? And if you look back at that, I've got a quarter wave on one side and I've got a quarter wave on the other side. So you add them together and it's a half wave. What wave are we talking about? We're talking about the wave that is associated with the particular frequency that we're transmitting on, right? So if I'm transmitting at 7.62 megahertz, right? Let me get my calculator out. It'll be 7.62 divided by 300. So that wave is going to be, no, I did that the wrong way. 7.6, it's 300 divided by 7.62. It's going to be 39 meters long, 39.37 meters long. Okay. That's how long a full wave is, from one end to the top, back to the bottom, and back to the middle again. 39 meters long. It's going to be in the 40-meter band, right? That's what we would call it. It's a 40-meter band. Depending on what frequency I'm trying to transmit at, that defines the band characteristic, which band my signal is going to go out on, and it defines the wavelength. Remember, the wavelength, the speed of light, and the frequency are all related together. If you multiply the frequency times the wavelength, you get the speed of light. So we measure our frequency in hertz, which is per seconds, or the reciprocal of seconds, or however you want to picture that. We measure the wavelength in meters typically, and then the speed of light is about 300,000 meters per second, something like that. So that's not exact. It varies depending on the medium the signal is, the radiation is traveling through, but that's a good enough estimation for what we're working with here. Okay, so that signal is carried at a particular wavelength or particular frequency down the wire, which causes the energy to come out in a particular wavelength. If my antenna doesn't match the length of the wave, then some of that energy is going to get reflected back from the end of the antenna. Because remember, the antenna goes out and it stops. It doesn't go on for an infinite length. And it's been worked out experimentally, and then the physics has been shown to prove it, that a quarter wavelength is pretty efficient in this. A full wavelength antenna would probably be the most efficient. But when you're talking about 40 meters, you're going to end up with 40 meters of wire on one side and 40 meters of wire on the other side. I don't know who has a backyard that's 80 meters wide, but that's a bit of a stretch, right? So You'll see people talk about, well, this is a half wave antenna, this is a quarter wave antenna, this is a 5/8 wave antenna, and you'll hear various descriptions of antennas. And each one of those has a different efficiency or a different capability of getting the energy out. Okay, so if it doesn't match, then some of that energy gets reflected back down the wire, goes back down the feed line and back into the radio. So we don't want that, because once it gets back into the radio, it's going the wrong direction and it turns into essentially wasted energy. It turns back into heat again. And if there's too much of it, it can actually damage the components inside the radio. Ragnar, go ahead.
I really understood antennas and the wavelength and the whole thing because I play my bass. And bass is a long wire and it resonates. However, I put my finger to get a full wavelength. Well, the bass is the lower frequency. A lot of people have trouble listening to lower frequencies, and tuning is harder. Well, if I touch my finger halfway through the string, I get a harmonic, which is basically a half wavelength antenna.
Where the waves reinforce each other.
Yeah.
Yeah.
So both ends, both halves of the string vibrate, but they don't vibrate in the middle. But they both vibrate, but they're twice as high in frequency, so to speak. But I found out I could take it down even more and get a quarter of it vibrating. It's funny, the top will vibrate like 3/4 of it vibrates and the quarter vibrates, but they're vibrating at different frequencies instead of like cutting it in half. But it helped me understand a lot how this antennas work, and knowing that, like, I can make a glass sitting over there vibrate
By picking just the right frequency, right?
It works. That's how the radio, and it sets out a vibration signal, and then you try and copy that same vibration in your antenna. Sometimes you have to change a whole bunch of things to make it the same. That's basically all I'm trying to do with the antenna. Make it the same way by manipulating all these things.
Right, right. So for those on the Zoom, Ragnar was talking about how when he plays his bass guitar, he can adjust the wavelength by where he puts his finger on the fretboard, right? And he can have like a half wave where he's actually changing the dynamic or the harmonic of the wire, the string on the radio, on the guitar, the bass. Oh, you play like a string bass. Okay, so on the
I play the upright most.
Okay.
I play electric too, but you
So-
can notice on the upright because it doesn't have frets.
and so he can feel that vibration and get an understanding of how that builds and how it wanes, right? And depending on where you put your fingers, you can either get a really strong signal off of that or less strong, right? And that's the same kind of thing we're doing with the antenna, is based on how long that antenna wire is. It's going to either reinforce or tear down that harmonic within the wire, right? All right, let's move on a little bit. We're going to talk about that a little bit more. What if our antenna is the wrong length? So what if I have an antenna that's set up for, or that's resonant or works well at 15 meters, but I want to use it on 40 meters? We can use a device called an antenna tuner, which actually adjusts the impedance to force the antenna to match the signal. Now, some energy is still going to get lost, right? It's not perfect. It's not magic. It can't magically make the antenna be right. But what it does is it uses an electrical property called reactance to counteract the impedance. And so if you opened up an antenna tuner and looked inside it, you're going to see a bunch of coils and a bunch of capacitors that are set up in a network, and the antenna tuner switches in between them and adjusts how much capacitance is being used and how much reactance is being used by the coils, being generated by the coils, in order to make that antenna look like it's the right length to the radio. So what it does is it helps get as much energy as possible out of the antenna. Now, again, it's not perfect, but I've seen things where like somebody was in an HOA environment where they couldn't have an antenna on their house. And what they did was they hooked their radio up to the rain gutter. And the rain gutter is made out of metal. And so it acted as an antenna or radiating element. Now, it obviously wasn't the right length. It wasn't the right shape. It didn't have a lot of the properties that you want in your antenna to be very efficient. But with an antenna tuner, this particular operator was able to get it to actually get a signal out. And that's really what we care about, is getting our signal out and getting a received signal back in. So let's talk a little bit about SWR. You guys all heard of SWR before? SWR is the standing wave ratio. And when we talk about antennas and we talk about how good they are in antenna systems and feedline systems and all of this, we talk about how good they are in terms of the standing wave ratio, the SWR. And a lot of people will have an SWR meter that will show them what that is. And a lot of radios nowadays have that built into them. So the radio will show you, oh, my SWR is this or that or whatever. If you think about it, I'm sending my signal out down this wire and out into the antenna, and some of that signal is bouncing back, right? That's the reflection in this diagram. If you combine those two together, you reach a place where you have a standing wave that represents the difference between those two things, essentially. If things aren't balanced, you're going to get a bigger amount of reflection, right? If your antenna isn't the right length, you'll get more reflection back from it, and your ratio or your standing wave will be bigger, right? So what is bad in an SWR? So typically we talk about SWR as a ratio, like 1:1, or as it's written here, 1:1. And 1:1 is perfect. That's the ideal, right? Every piece of energy I send out is going out. None of it's reflecting back. Now, if I see like 1.1 or 1.2, I'm wasting some energy. Some of my energy is not getting out, but it's still probably okay. Up to about 1.5, it's not going to hurt your radio, right? But when you start getting SWRs of 1 to 2, 1 to 2.5, 1 to 3, that's not good, right? Your radio can probably still tolerate it for a period of time. You know, if you really got to transmit something in a hurry and you don't have an antenna tuner and you're running off of your rain gutter and you look at your SWR and it says, oh my gosh, it's 1 to 3. But if I keep my transmission short, I can still make my transmission. But I'm not going to sit there and talk for 10 minutes on it, right? Because that's every piece of that energy is coming back into the radio, is causing things to heat up inside the radio and can cause damage. SWR only affects you on transmission. It has no effect on reception at all, on receiving the signal. The signals coming in from the antenna are so weak that they can't cause any kind of damage to the radio. Okay. You got a funny look on your face, Jeff.
It's okay.
Okay, let me qualify that and say, if I'm standing right next to Sherwood and I key up my handheld on the same frequency that his radio is trying to receive, his radio is not going to receive it because it will be getting so heavy of a blast of energy from my radio that it will desensitize his receiver and it won't be able to pick the signal out. It's like if you were, think about if you're in a band and some guy is playing the trumpet, right? And you're sitting in the audience and you can hear the trumpet and it sounds really nice. But if you were to walk up to the orchestra pit and stand with your ear right next to the trumpet, you're not going to get a nice experience, right? It's the same kind of thing. So even though he's playing just as nice as he was, when you're that close and there's that much power hitting you, it's going to be bad news. But in general, your receiver is not going to get overwhelmed by the signal that's coming in. Now, if the signal is coming from a lightning bolt or something, okay, it's going to get overwhelmed by that, right? In fact, it's probably going to get slagged by that, but we're not going to worry about that. Okay, so how do I fix a high SWR condition? I basically have two choices. I can adjust my antenna to better match the wavelength that I'm trying to transmit, or I can use an antenna tuner to try to match that impedance in circuitry. All right. It's going to be different depending on what band you're on. If I'm on 40 meters, I may not need any, my SWR may be fine, right? Because of the nature of the antenna. Whereas if I switch to 20 or 15 or some other band, that particular antenna might not work very well without some major manipulations of the signal. Okay. And this is why when we look at our, when you buy your typical tri-band handheld, right, it's going to work on 2 meters and 70 centimeters. And then we want it to also work on the 1.25 meter, right? 2 meters and 70 centimeters actually line up pretty well in that what ends up being like a quarter wave for 2 meters ends up being about a half wave for 70 centimeters. And so the same antenna works pretty well on both of those. But if I try to lump 1.25 meters into the mix, all of a sudden it's not that great. Now you can buy an antenna, and Bruce has one, that actually supports all 3 bands. And it does that by adding some load coils in the base of the antenna that you can't see because it's inside the antenna. But that's why that thing is like 1.5 inches long down there at the bottom, rather than just being, you know, the wire going directly into the connector. I wish I'd brought my signal stick with me, because then I could have shown you the difference between a dual band antenna. Yeah, so it's got, and that's there specifically to help match the impedance of the 1.25, right? So that's something you need to consider when you're working with an antenna, is what bands does this antenna support, and what do I need to do to make it actually work? There's a guy who's producing a dipole antenna, which is basically just a long piece of wire with a connector in the middle, right? And it's set up for multiple bands. And the way that it's set up to do that is at various lengths along that wire are little connections. And if you disconnect that, now the antenna is shorter and it's better for a different band. So you just have to make sure you make the appropriate connections for the band you want to use.
You can do that with the track.
Or you can do that with a track, right?
My vertical has four bands.
Remember, receiving is different from transmitting, because the receiving will just work. Go ahead, Ragnar.
It also depends on the environment that you're antenna in. Like I have a 49-foot tower.
Mm-hmm.
And on it, basically a dipole thing that works for several bands.
But if it was close to the ground, it wouldn't work as well.
It did. I don't know what happened. It didn't install. It's supposed to do it by the good heights, but certain trees around, the cooler on my house, many things. I tried everything to do it anyway. I went with a vertical 10-meter, it was fine, but for some reason, so it's a lot of environmental on the way you set up your antenna.
Yeah, so Ragnar points out that the environment where your antenna is can have a lot to do with how well it works as well. It can be affected by proximity to the ground or to other metallic objects, or even to things like trees or buildings or something like that. If they're in close proximity to the antenna, they can have a major effect on how that works. All right. So let's talk about some different antenna types, and let's talk about how they emit radiation. So remember, the things there's a few factors that go into picking an antenna for what you're trying to accomplish. Those things are the polarization of the signal, directionality of the signal, and gain on the signal. We're going to talk about each of those. All right. So let's talk about polarization. Do you guys understand what polarization means? Have you ever worn like polarized sunglasses and taken like, or have you ever gone like to the 3D movie at the theater and they give you the little glasses to wear? And if you take your glasses and somebody else's glasses and hold like the left lens over the right lens, you can't see anything through it. Right? Have you ever done that? Sunglasses will be polarized as well. In aviation, they recommend that you don't wear polarized sunglasses because it could affect your visibility of the instruments and of things in the environment, right? So they recommend not doing that. In your car, for example, typically the rear window has varying polarization in it. So if you're wearing polarized sunglasses and you look out the rear window, it's got this kind of mottled or splotchy appearance. You take your sunglasses off and it's perfectly clear. You can see through it just fine. What polarization refers to is what pattern that wave is as it leaves the source. If it's horizontally polarized, it's going to be like flat, right? If it's vertically polarized, it's going to be up and down. So if I've got my handheld and it's got a antenna sticking up and down, what way do you think my signal is going to be polarized? Vertically, right? If I've got my dipole stretched out in my backyard from one point to another, and one end point is 30 feet away from the other end point, how do you think that's going to be polarized? Horizontally, right? There are also some weird polarizations like circular polarization, which is really confusing to visualize how that's actually generated by the antenna. But essentially, the signal is moving in a helical or corkscrew fashion. And you can have right hand or left hand. These are typically used in satellite communications. There's also, you'll find equipment that does dual polarization. So it may be both horizontal and vertical. You'll see that with Wi-Fi, for example. Wi-Fi will typically, they'll have some of the signal that's vertical and some of the signal that's horizontal. And they do that because they don't know what orientation your receiving device is going to be in. And so they want to get as much signal to you as possible. So they split the signal and do half of it vertical and half of it horizontal. You might see this cross polarization as well, which is just rotating that 45 degrees, right? So part of the signal is polarized this way, part of it's polarized this way. It's not perfectly efficient in either direction, but if you don't know which way your antenna is pointing when you're receiving, the receiving antenna is pointing, it's a good compromise, right? When we're talking to somebody on the repeater and we can't hear them very well, sometimes it is helpful to ask them to make sure they're holding their radio straight up and down, holding their handheld straight up so the antenna goes straight up and down. That's because the antenna at the repeater site is vertical. So if their antenna is also vertical, then more of the energy will get received by that antenna than if they were holding their radio sideways. Now, how many times do you see somebody pick up the radio on movies and they're holding it like this, the antenna sticking out that way? That's like the least efficient way to do it. So we don't ever do that, right? Okay, maybe not never, because it, you know.
Unless the person you're talking to is holding it the same.
Unless the person you're on not on a repeater and you're talking simplex to somebody and they're holding their radio sideways, so you got to hold yours sideways. What if they're holding it at 38.2 degrees and you got to get yours lined up just so, right? So that you get lined up with them. But yeah, so you can have your radio polar, your signal, your antenna polarized in a particular fashion. This affects not only how much power gets picked up by the receiving antenna, but also how well the signal propagates, right? Another thing that we talk about with antennas is directionality. So some antennas have a preference or a bias to send more of their energy in a particular direction, while others are omnidirectional. Now, I say omnidirectional. The only true omnidirectional antenna is a ball-shaped antenna, okay? That's going to actually send the signal in every direction at once. But I say that that vertical antenna on Sherwood's radio is omnidirectional because it's sending the signal out in all directions around me. It's not sending as much energy straight up as it is sending out sideways, but I call it omnidirectional because I think two-dimensionally, not three-dimensionally, right? So some antennas are going to have a strong bias to send energy in one particular direction, and others are going to be more willing to send it in multiple directions. So if we look at a few different antenna types, a dipole is going to have kind of this figure eight structure, and less energy is going to be sent in the direction the wire is pointing, and more energy will be sent out from the sides of the wire, if you picture it that way. So this would be like looking top down on the antenna, right? So if I have my dipole strung up across my yard and the one wire is pointing north and the other wire is pointing south, I'm not going to be able to hit somebody at the North Pole or the South Pole very well with that. But my energy will be going east and west, which is where I want it to go, right? With a Yagi antenna, Yagi is a very directional antenna. It uses a driven element, a reflecting element, and then directing elements that help focus that energy as it leaves the antenna. So some energy still leaks out the back, but most of the energy goes in one particular direction. So you'll typically see like a TV antenna is going to be a Yagi type antenna. And if you point it at the transmission tower, you're going to pick up a better signal than if you're pointing it some other direction, right? Same thing goes with transmitting it. And of course, a dish antenna or a parabolic antenna is going to be very focused. Almost no energy is going to leak out the backside of that. Almost all of it is going to go in the direction the antenna is pointing, right? So direction matters depending on the type of antenna that you're using. Yes, Ragnar.
There's also an angle of,
Incidence, right? So
some.
do I want my energy going up or down or straight out or what, right?
Like you do local. And you get an antenna that points the signal like 45 degrees or 30 degrees up. You'll be fine a long ways away, but
you won't catch anybody close to you, right? Yeah. And so there are antenna types they call NVIS. I don't remember what NVIS stands for, but near vertical incident something, right? Yeah. So the idea there is that the signal travels almost straight up and down. And so it travels up into space, hits the ionosphere, and bounces back straight down. And so it doesn't go far away from where I'm at, maybe 100, 200 miles, not 1,000 miles or 10,000 miles, right? Whereas if I've got my dipole and it's sending most of that signal out in a straight line, remember the Earth is curved. So as my signal goes out, it gets farther away from the ground as it goes out, right? Or the ground gets farther away from it, I guess you'd say. Eventually it hits the ionosphere and it bounces and comes back, and it's going to be, you know, several hundreds or thousands of miles away from where I'm at. You may also get bouncing multiple times, get your signal to actually go multiple times. So Ragnar, another comment.
That kind of antenna was used a lot in Iraq and there at the deserts, and they're basically thrown on the ground, and the signal goes up and covers you a couple hundred miles. It doesn't go anywhere else. So the military used that a lot.
So Ragnar points out that the military used those NVIS type antennas a lot to keep that signal in their area of operation, right? So you're not sending the signal much farther away than you need to. You want to keep it relatively local.
You look at the antennas and they don't look like an antenna because they basically just throw a bunch of wire on the ground. And it works just fine for that.
Okay, so the next thing, so we talked about polarization, we talked about directionality. The last thing is gain. And if you think about this, think about that focused antenna, that Yagi antenna that's focusing the energy, or the parabolic antenna that's really focusing the energy in a particular direction. I'm putting the same amount of energy into my, out of my radio and into my antenna. So if I've got a parabolic antenna, 100% of that energy is going to be going out the direction the parabola is pointing, right? Whereas in my dipole, it's more spread out. So I don't have as much gain on that. Now, other factors also apply, like the length of the antenna, how close it is to the wavelength that you're doing, which you're working with, if it's balanced or not. All of those things will affect the gain as well. And just as an example, on our repeater, Murray Amateur Radio Club's repeater, the antenna actually gives us a significant amount of gain, not only because of the physical antenna itself, but the fact that it's 200 feet up on a tower also gives us a significant amount of gain. So the radios in the repeater are only putting out like 25 watts, but when it's emitted from the antenna, it's like 350 watts of effective power coming out of that repeater. So that's something that you want to take into account as you're designing your antenna system or setting up your antennas. All right. So that covers pretty much everything I wanted to talk about. Basically, antenna theory is complicated. There are software tools you can use to help you design antennas and make them work on particular bands and things like that. It's not trivial to understand the physics behind this and to figure out how everything actually works. I did set up a YouTube playlist. I will put a link to this on the website, as well as you'll have the link in the presentation. There's several videos in there that are pretty good as far as talking about the nuts and bolts of what's happening inside the antenna, how it's actually working in the physics, and how different types of antennas affect your signal, and how you should set up your antenna, how to arrange your antenna to get the signal where you want it to go, and things like that. But that's about all that I have. So I will wrap it up here, and I'm going to stop the recording.